Today we're going to be looking at a series of videos talking about multiplying and dividing complex numbers. So our first theorem here is called the multiplication theorem. And the multiplication theorem says that if you have two complex numbers in trig form, then it's going to be really easy to divide those and multiply those together. So in this case, we have z1 and z2. And remember, we can write them in trig form using their moduli. So that's r1 and r2. That's really the distance they are away from that zero in complex plane. And their argument, that's the angle from the real axis. It's going to be positive if we're going counterclockwise, just like a lot of things that we've been looking at in this class. It turns out that if we multiply those two numbers together in trig form, then we can end up multiplying their moduli and then adding their arguments. So that's a really slick way to go ahead and put these together. It really comes from the fact that you have two complex numbers and we use those addition and subtraction of sine and cosine that we learned way back in chapter 5. So let's look at an example using this. So we want to find the product of z1 and w2, then convert the trig to trig form and find the product again. Finally, we'll convert that answer to a standard form and show that their products are equal. So let's go ahead and convert these to trig form. So if I go ahead and sort of draw these out, it's always a good idea. I have z1, which is over 2 root 3 and up 2i, so that would be right around here. And z2, which is over the same distance in the real axis and then down in the imaginary axis. So here would be w2. Remember, we can go ahead and construct that triangle out there. So when we look at that, we have 2 root 3 in the real plane, and we have 2 in the imaginary plane. So when we're thinking about this, let me draw my 2 there, we have one of those special triangles in ratio of 1 to root 3 to 2. So we could go ahead and say the smallest side is 2, the bigger side is 2 root 3, so using our ratio 1 to root 3 to 2, this is going to be 2 times the smallest side, or 4. So our modulus of z1 is going to be 4. You could also get that definitely by the Pythagorean theorem. Now if I look at w2, everything is the same, except for I go down 2. So we know that the modulus of w2 is going to be 4 as well. Finding their angles, again, we can use that idea of a 30, 60, 90 triangle. So we're across from the smaller side here. So if I'm looking for my argument, I know that's just going to be 30 degrees. And I'm going to have the same reference angle down here in quadrant 4. So if I spin all the way around, I'm going to have theta is equal to 360 minus 30, or 330 degrees. So I can put those together. I know that my modulus is 4 for the first. So z1 is going to be equal to 4 cis of 30 degrees. And w2 is equal to 4 cis of 330 degrees. So now that I have those, I'm going to switch over. I'm going to do a new share here. And we're going to be looking at multiplying these together by the theorem. So notice I put my multiplication theorem up there. I have my two numbers, but we converted those into trig form. So my Z1 was 4 cis 30 degrees, and my W2 was 4 cis 330 degrees. So if I can convert those into trig form, look how easy it is. I multiply those together by taking the product of their moduli. So Z1 times W2 is equal to the product of those moduli. And then I just add their angles together. So I have cis of 30 degrees plus 330. And I get 4 times 4 is 16. I get 30 plus 330 is 360 degrees. So that is going to be my number in trig form. So what I would do is notice I have my 30 degrees here. I add on my 330, and that's going to put me right on my real axis. It's going to be the 360 degrees around. And I'm going to go out 16. So I think I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my new number, that product, is going to be right over here. And it really is just going to equal 16. And you can definitely see that if we convert that trig form back into a standard form. So I'll have 16 times the cosine of 360 degrees plus I sine 360 degrees. I know that the cosine of 360 degrees is just like the cosine of 0, so that's just going to be 1. And the sine of 360 degrees is like the sine of 360 or 0. It's going to be 0. So I have 16 times 1 plus I times 0 equals 16. Now, another way we could do this is by the standard way, so not converting them. So I have 2, if I do it that way, I have 2 root 3 plus 2I times 2 root 3 minus 2I. I can distribute through, so 2 root 3 times 2 root 3 is 4 times root 3 times root 3, which is 3. And then I multiply 2 root 3 times negative 2i, that's negative 4 root 3i. And I multiply 2i through, so 2i times 2 root 3 is going to be plus 4 root 3i. And then finally, 2i times negative 2i is a negative 4i squared. These two are going to subtract out, so my number is going to be all real, like we sort of knew that that was going to happen, right? And then my I squared, I can plug in a negative 1. So I have 4 times 3 are 12, minus 4 times negative 1, which would be 12 plus 4 or 16. So we get that number back. You might want to notice that this is a number times its conjugate. Graphically, we can sort of see that when we take a number times its conjugate, we're always going to have that imaginary part goes away. That's why we take a number times its conjugate. So when you're adding these up, you could sort of think of it as a 30-degree angle plus a negative 30-degree angle, if you want to think of it that way. And so when you add those together, we get 0 degrees, and that you multiply the moduli, which were 4 and 4, so you'll get 16 there. Pretty cool, right? Okay, let's look at another example here. I'm going to try to zoom out a little bit. So in example 2, we're going to be using this multiplication theorem again, and I already have these numbers in trig form. So I have 2 cis 7 pi over 4. I've written that over here, so there is my 7 pi over 4 angle, and then I have 8 times cosine of 270 degrees plus I times sine of 270 degrees. So 270 is going to be one of those quadrantal angles, and it's going to put me down here. with a modulus of 8. Okay, so I can use this multiplication theorem to multiply these together. W1 times Z2 is equal to, I multiply the moduli together, so I have root 2 times 8. And I'm going to use this, I guess, abbreviated notation. So I'm going to take 7 pi over 4 plus 270. So I have things in different formats here. Which is going to be easiest to work with? I bet you would say degrees. So if I do use degrees, 7 pi over 4, reference angle is pi over 4, that's 45 degrees, but I'm over here in quadrant 3, so that's going to be 315 degrees. Okay. So I'll just add those together. So I'll have 270 plus 315 degrees. All right. So I will get 8 root 2 for my modulus. I'm going to add these two together. So that would give me 5 and 8 and 5. So 585. I'm not really sure where that puts me. I know it's somewhere between 360 and 720. So I might want to just subtract 360 from this to figure out what angle is going to be coterminal to that. So if I subtract off that 360, I get 225, and now I know exactly where I'm at. So this one's going to be 8 root 2 times the cis of 225 degrees. So if I wanted to illustrate the product, I could do that. I know 225 degrees is going to put me smack dab in the middle of quadrant 3, and I go out 8 root 2. Root 2 is about 1.41, so we're roughly looking at 12 units away, so that's going to be pretty far out there. Maybe like right around here. So this is going to be our product out here. All right, and if you wanted to convert that back into a standard form, you could do cosine of 225, which would be negative 1 over root 2, plus I sine of 225, which would also be negative 1 over root 2. Multiply the 8 root 2 through, and you get negative 8 minus 8i. Very cool. All right, we'll look at another video in just a minute about the other aspects of this. Thank you.